Welcome back to the deep dive. Usually when we talk about the human body, we talk about organs, the heart, the lungs, the brain, big, tangible structures.
Right. Things you can, hold in your hand, conceptually at least.
Exactly. But today, we are going to talk about a liquid organ.
Uh-huh.
We are talking about blood. And I don't mean just the red stuff that comes out when you cut your finger. I mean looking at blood as a biological crime scene.
It's a very, very apt metaphor.
You think so?
Oh, absolutely.
Yeah.
Because if you know how to read the evidence, blood tells you exactly what has happened, what is happening, and sometimes what is about to happen to a patient.
It's wild. I've been poring over these hematology case reviews and protocols, and it struck me that a single drop of blood is basically a bustling metropolis.
I love that. A metropolis.
You've got different citizens with different jobs, you've got supply chains, trash removal, and, occasionally you have terrorists or structural collapses.
That is the perfect way to visualize it. I mean, hematology is unique in medicine because the pathology is often visual.
Right. You're literally looking at the problem.
We are. We aren't just looking at numbers on a spreadsheet, although we have plenty of those. We are looking at the morphology, the shape and size of the cells themselves.
And that's what we're doing today.
We are decoding the clues hidden in the red and white blood cells to distinguish between something benign, like a simple vitamin deficiency, and something catastrophic, like acute leukemia.
And that's our mission today. We are going to decode those clues. We're going to start with the physics of the lab bench, because apparently gravity matters.
Oh, it matters a lot.
Then move into the geometry of red blood cells, explore the warfare of the white blood cells, and finally get into the heavy genetic stuff that defines cancer.
We have a lot of ground to cover. We're going to go from really simple arithmetic to complex chromosomal translocations.
Okay, let's do it. Let's start at the very beginning. The sample itself. I always thought you just draw blood, put it in a machine, and boom, results.
That's the dream.
But reading about the mechanics of centrifugation changed my whole perspective. The spin itself is a variable.
It is the foundation of everything.
Yeah.
When we measure the hematocrit, the HTT, we are measuring the volume of packed red blood cells relative to the total blood volume.
The percentage of red stuff.
A percentage of red stuff, exactly. And to get that number physically, you have to use centrifugal force to pack those cells down at the bottom of the tube.
Right. And here is where the physics gets tricky. If you don't spin it fast enough or long enough, you get what the source calls insufficient centrifugation.
Right. And that's a huge problem. Imagine filling a jar with marbles.
Okay.
If you just pour them in, there are gaps of air between the marbles. But if you shake the jar or vibrate it, they settle closer together, minimizing those gaps.
So the spin is the shaking.
The spin is the shaking.
Yeah.
In blood, if the centrifuge stops too early, you have trapped plasma liquid remains stuck between the red blood cells.
And because that plasma takes up space, the layer of red cells looks taller than it actually is.
Correct. Which gives you a falsely increased hematocrit.
Wow.
So you might think a patient has normal blood volume or even polycythemia, too much blood, when in reality, your machine just didn't spin the sample hard enough.
It's a great reminder that even in high-tech medicine, basic physics still rules.
Always.
But let's assume we get the spin right. We get these numbers, the hemoglobin, the hematocrit, and the red blood cell count. This leads us to the indices.
The red cell indices. This is the first step in profiling the suspect, to go back to your metaphor.
And this brings up the rule of 3. I love this because it feels like a cheat code for the lab tech.
It's a vital quality control check. It's not so much a biological rule as it is a mathematical sanity check.
How does it work?
In a healthy person with normal red blood cells, the hemoglobin value multiplied by 3 should roughly equal the hematocrit.
Okay, HGB times 3 is HTT.
Roughly, plus or minus a few points. And the red blood cell count multiplied by 3 should roughly equal the hemoglobin.
So it's a lie detector for the machine.
In a way, yes. If your machine tells you the hemoglobin is 10 grams per deciliter, but the hematocrit is 45%, the math is broken.
Because 10 times 3 is 30, not 45.
Right. That discrepancy tells the scientists, stop. Something is wrong.
And what could be wrong?
It could be a problem with the sample itself. Maybe it's full of fat. We call that lipemia. Or maybe there are cold antibodies making the cells clump together, which messes up the count. It forces you to investigate before you release a result that might lead a doctor down a completely wrong path.
Okay, so once we trust the numbers, we start calculating the profile of the cell itself, the MCIV, MCH, and MCHC.
Yes.
Let's break these down because they seem like just acronyms, but they're actually descriptions of physical reality.
Let's start with MCV. That's the mean cell volume.
The average size.
It is quite simply the average size of a single red blood cell. We calculate it by taking the hematocrit, dividing by the red blood cell count, and then multiplying by 10.
And the unit is femtoliters, which is just, we are talking about 10 to the negative 15th power of a liter. It's mind-blowing that we measure volume at that scale as a routine diagnostic.
It is incredible precision. And it's so important. A normal red blood cell should be between 80 and 100 femtoliters.
That's the normal range.
Right. So if the MCV is 70, the cells are microcytic, they're tiny. If it's 115, they are macrocytic, huge. This number alone is the first major fork in the road for diagnosis.
So just from that one number.
Just from that, if I see an MCV of 70, I'm immediately thinking about iron deficiency or maybe some genetic globin issues. If I see 115, I'm thinking about liver disease or problems with DNA synthesis like B12 deficiency.
So MCV is the size of the house. Then we have MCHC, mean cell hemoglobin concentration. This is how packed the house is.
That's a great way to put it.
Yeah.
Think of it as the density of the color inside the cell.
Okay.
It's the ratio of the hemoglobin weight to the volume of the cell. The formula is hemoglobin divided by hematocrit times 100. It gives you a percentage.
And what's normal?
Normal is roughly 32% to 36%.
And if it's low?
If it's low, the cell is hypochromic.
Zest color.
Exactly. Under the microscope, red blood cells usually have a small area of central power, a little white spot in the middle, kind of like a donut.
Right.
In hypochromic cells, that white spot gets huge because there just isn't enough red hemoglobin to fill the cell. It looks like a thin red ring.
And finally, MCH, mean corpuscular hemoglobin.
This is the actual weight of hemoglobin in an average cell.
Not the concentration, but the raw weight.
Right. The formula is hemoglobin divided by the RBC count. It generally tracks with the MCV. It makes sense, right?
Yeah.
Smaller cells usually weigh less.
Okay, so the material had us do a calculation. Hemoglobin of 15, hematocrit of 47, and an RBC of 4.5.
Right, so let's run the numbers. For MCV, you take 47 divided by 4.50.
That's about 10.4.
Yep. Multiply by 10, and you get 104 femtoliters.
So just a little on the large side, slightly macrocytic.
Exactly. Now for MCHC.
That would be 15 divided by 47.
Which is about 0.319. Multiply by 100, and you get 31.9%.
So just a hair low, basically normochromic or normal color.
Right. These calculations happen instantly in the analyzer, but understanding why they move up or down tells you the pathology.
But averages can be tricky, right?
How so?
Well, if I have a room full of toddlers and NBA players, the average height might look like a normal adult, but the reality is totally different. No one is actually average height.
Precisely. That is a perfect analogy.
Yeah.
And that is why we look at the RDW.
The red cell distribution width.
Yes. It measures the coefficient of variation. If every cell is exactly the same size, the RDW is low. But if you have tiny cells mixed with huge cells, your toddlers and basketball players, the RDW will be high.
And we call that variation.
Anisocytosis.
Anisocytosis. It sounds like a complex disease, but it really just means unequal sizes.
Correct. And that is different from poikilocytosis.
Which is?
Variation in shape. Not size, but shape. Sickle cells, sphere-shaped cells, fragmented cells. That's poikilocytosis.
Before we get into those shapes, I want to touch on one chemical detail regarding the microscope slides themselves.
The stain.
The stain. We use a right stain to make these cells visible, but apparently the pH of the dye is absolutely critical.
It's chemistry in action. The stain has two main components, methylene blue, which is a basic dye, and eosin, which is an acidic dye.
Opposites attract.
Exactly. So things in the cell that are acidic, like the DNA in the nucleus, will attract the basic blue dye and stain purple.
Okay.
And things that are basic, like hemoglobin, will attract the acidic red dye, eosin, and stain pink or red.
But what happens if the pH is off?
Well, the source mentions if your buffer solution is too acidic, say the pH below 6.4, the red cells will take up too much eosin. They turn this bright, angry pink.
And that's not just a color preference problem.
No, the real loss is in the white blood cells.
Yeah.
The nuclear detail, the chromatin patterns that help us identify the cell gets washed out. You can't tell a monocyte from lymphocyte if the nucleus is just a pale ghost. You need that perfect pH balance to see the crime scene clearly.
So we've got the physics and the chemistry down. Now we look at the suspects. Section 2 is the red cell spectrum, specifically the anemias. Right.
And we organize these by size based on that MCV number we just calculated. Let's start with the small ones. Microcytic anemias.
When a cell is microcytic, it means the bone marrow didn't have enough ingredients to build a full-size cell. It stopped growing early.
Something was missing from the assembly line.
Exactly. And the most common cause globally is iron deficiency anemia, or IDEA.
This seems straightforward. You don't have enough iron, so you can't make hemoglobin, so the cells are small and pale.
Microcytic hypochromic. That is the visual result. But the biochemical profile is fascinating.
Only.
In IDEA, obviously your serum iron is low. Your ferritin, which is the protein that stores iron in your tissues, is also very low. That's your iron savings account, and it's empty.
Makes sense.
But then look at the TIBC total iron binding capacity.
It goes up.
It skyrockets. Think of TIBC as a fleet of empty buses sent out by the liver to pick up iron. The protein is called transferrin.
Okay, transferrin is the bus. Right. In IDA, the body is desperate. It's screaming, we need iron. So it manufactures more and more buses, but there are no passengers. So the capacity to bind iron is huge, even though the iron itself is absent.
That makes perfect sense. But here is the nuance that blew my mind. There's another condition called anemia of chronic inflammation, or chronic disease.
Ah, yes. The great imposter.
The cells can look the same, sometimes small and pale. The serum iron is also low, but the mechanism is totally different.
This is one of the most clever evolutionary mechanisms we have. Bacteria and cancer cells need iron to thrive and reproduce.
They need it just like we do.
They do. So when the body detects a chronic infection or severe inflammation, it assumes it is under attack. The liver produces a peptide called hepcidin.
Hepcidin.
Hepcidin acts like a locksmith. It goes to the cells that hold iron, the macrophages in your spleen, the cells in your gut lining, and it locks the doors. It sequesters the iron, saying, we are not letting the bacteria get this fuel.
So the iron is there, it's just locked in a safe.
Exactly. So in this case, the serum iron is low because it's all hidden away. But, and this is the key differentiator from IDA, the TIBC is low or normal.
Why?
The body isn't sending out more buses. It's intentionally shutting down the transit system to starve the invader. It knows where the iron is, it's just not letting it out.
That is brilliant. So if I'm a doctor, high TIBC means the body is hungry, so it's iron deficiency.
Right.
Low or normal TIBC means the body is hiding resources, so it's chronic inflammation.
Precisely. It's a beautiful piece of diagnostic logic.
Now, what if the cells are tiny, but the iron levels are totally normal? The factory has the raw metal, but the product is still coming out wrong. This leads us to thalassemia.
Thalassemia is not a supply problem, it's a blueprint problem. Hemoglobin is made of 4 protein chains, usually 2 alphas and 2 betas. In thalassemia, you have a genetic deletion or a mutation. You literally cannot manufacture enough of one of those chains.
So it's a quantitative defect. You just don't have the parts.
Exactly. And the body tries to compensate. If you have beta thalassemia, you can't make enough beta chains.
Yeah.
So the body will try to make other chains, like delta or gamma chains, leading to increases in hemoglobin A2 and hemoglobin F.
And hemoglobin F is fetal hemoglobin, right?
Yes, it's what we have in the womb.
Yeah.
In beta thalassemia major, where you make almost no beta chains, you'll see very high levels of HGBF as the body desperately tries to make some kind of functional hemoglobin.
But what about the alpha chains?
Ah, that's the tragedy. You keep making alpha chains at a normal rate. But these excess alpha chains have nowhere to go. There aren't enough beta chains to pair up with.
So they just float around.
Worse, they precipitate inside the red blood cell, forming inclusions that damage the membrane. This leads to the cell being destroyed before it even leaves the bone marrow.
This is called ineffective erythropoiesis.
Yes. The marrow is working overtime trying to compensate for the anemia. That's why, paradoxically in thalassemia, you often see a normal or even high red blood cell count.
That's so counterintuitive.
It is. The marrow is just churning out millions of these tiny defective short-lived cells. Yeah. So, low MCV, but high RBC count. That is a classic thalassemia signature.
And unlike IADA, giving these patients iron won't help. In fact, it could hurt them.
It could cause iron overload, which is toxic. You have to get the diagnosis right.
There is one more microcytic anemia that has a very distinct visual, sideroblastic anemia.
This is a failure of the final step in the assembly line. It's a problem with the mitochondria.
Okay.
The iron is delivered to the cell. It gets into the mitochondria where heme is supposed to be made, but the enzyme machinery is broken. The iron can't be incorporated into the protoporphyrin ring to make heme.
So it just piles up.
Just piles up. So specifically, it piles up in the mitochondria, which are clustered around the nucleus.
And that's what we see.
Yes. When we stain the bone marrow with a special iron stain called Prussian blue, we see these blue granules of iron ringing the nucleus of the red cell precursor. We call them ringed sideroblasts. It's basically a cell choking on the iron it cannot use.
Okay, let's move up a size class. Normocytic anemias. The cells are the right size, but they are dying young.
Right. The factory's making them correctly, but they're not surviving on the streets.
This is the realm of hemolysis. And I want to talk about hereditary spherocytosis, or HS. This is a geometry problem.
It is, absolutely. A normal red blood cell is a biconcave disc like a donut without the hole punched all the way through.
Right.
That shape is crucial because it creates a high surface area to volume ratio. It allows the cell to be floppy and flexible,
Why does it need to be floppy?
to fit through the capillaries. Some capillaries in your body, especially in the spleen, are narrower than the red cell itself. The cell has to fold like a taco to squeeze through.
But in spherocytosis,
There's a genetic defect in the cytoskeletal proteins, usually spectrin or ankyrin. These proteins form the internal scaffolding that holds the membrane in that disc shape.
so the scaffolding is weak.
The scaffolding is weak. So as the cell ages and goes through circulation, it loses little bits of its membrane. And without that support, the membrane snaps into the most tension-efficient shape possible for its volume, a sphere.
And spheres don't fold.
Spheres are rigid. They have the lowest possible surface area to volume ratio. So when these cells travel through the spleen, which acts as a blood filter with tiny mesh-like slits called the cords of Billroth, they get stuck.
They can't squeeze through.
They can't. The splenic macrophages see them stuck there, recognize them as abnormal, and eat them.
So the spleen is doing its job, but the cells are failing the flexibility test. How do we diagnose this in the lab? The osmotic fragility test.
This is a fun old-school application of osmosis.
How's it work?
We put the patient's blood into a series of tubes with increasingly watery or hypotonic salt solutions. As the solution gets more watery, water rushes into the cells, making them swell.
A normal disc has extra skin, right? It's kind of baggy, so it can puff up a bit before it pops.
Exactly. It has slack. It can handle some swelling.
Right.
But a spherocyte is already a sphere. It has zero slack. It's maxed out on its volume for its surface area.
So as soon as water rushes in,
Pop. It laces. So if the patient's cells burst at a higher salt concentration than normal cells do, we say they have increased osmotic fragility.
and the cure involves taking out the spleen.
It's the standard treatment, a splenectomy. You aren't fixing the genetic defect. The cells will still be spheres, but you are removing the executioner.
You're removing the filter.
You're removing the site of destruction.
Wow.
Without the spleen to trap and kill them, the spherocytes can live a relatively normal lifespan in circulation.
From spheres, we move to the most famous shape in hematology, the sickle cell anemia.
This is a qualitative defect. Unlike thalassemia, where parts are missing, here the parts are there, but one of them is broken.
And so specific.
It is a single amino acid substitution on the beta-globin chain. At position number 6, glutamic acid is replaced by valine.
One tiny swap in a massive protein chain.
That's all it takes, and it's all about chemistry. Glutamic acid is polar, it's hydrophilic, it likes water. Valine is nonpolar, hydrophobic, it hates water.
Okay.
When the red blood cell is fully oxygenated, everything is fine. But when the oxygen level drops, like when the cell delivers oxygen to your tissues, the hemoglobin molecule changes shape slightly.
And that exposes the valine.
It exposes that hydrophobic valine spot. It seeks cover. It finds a complementary hydrophobic spot on a neighbor hemoglobin molecule, and they lock together.
They clump.
They polymerize. They form these long, rigid, crystal-like rods inside the cell. These rods physically stretch the cell's membrane into that crescent moon or sickle shape,
And this causes the crisis.
the vaso-occlusive crisis. These rigid sickle cells act like logs jamming a river. They block the microvasculature.
The tiny blood vessel.
Exactly. It causes ischemia, lack of oxygen to bones, organs, and tissues, and it is excruciatingly painful for the patient.
We diagnose this with electrophoresis. We race the hemoglobin.
Right. Hemoglobin has an electrical charge. We put a sample in a gel and apply a current. The charge depends on the amino acids.
And glutamic acid is different from valine.
Glutamic acid is negatively charged. Valine is neutral. So sickle hemoglobin, HGVS, is less negative than normal hemoglobin A. It moves slower toward the positive anode.
S stands for slow.
Exactly.
Oh.
And this helps us distinguish the trait from the disease. In sickle cell trait, heterozygous, the patient makes both types of chains. So on the gel, you see a big band at the A position for normal and a smaller band at the S position.
So they have a mix.
They have a mix, about 60% and 40%. They rarely have crises because the normal hemoglobin interferes with the polymerization process. But in sickle cell disease, homozygous, you see virtually no A, mostly S.
Before we leave the normocytic group, I have to ask about PNH, paroxysmal nocturnal hemoglobinuria. The name is a mouthful.
It's a fascinating, rare, acquired disorder. It's not inherited. It's a stem cell mutation that happens during your life.
What's the mutation?
The cells are missing a specific anchor, a GPI anchor, on their surface. This anchor normally holds a bunch of proteins onto the cell membrane, including two very important ones, CD55 and CD59.
Then what do those proteins do?
They are do not eat me signs for your own immune system. They protect the cell from complement.
Complement.
Complement is a part of our own immune system, a cascade of proteins that drifts in the blood, ready to punch holes in bacteria. CD55 and CD59 tell complement, hey, I'm one of you, I'm human, don't punch a hole in me.
So PNH cells are missing the shield.
Yes. So the body's own immune system attacks and lyses the red blood cells. It's an autoimmune hemolysis.
And why nocturnal? Does it only happen at night?
It's called nocturnal because historically we noticed patients had dark reddish-brown urine in the morning. During sleep, your breathing slows, your blood CO2 rises slightly, and your blood pH drops a tiny bit. This slight acidity activates the complement system more robustly.
The test for this used to be the sugar water test.
Or the Ham's test. Sucrose, or sugar, provides a low ionic strength environment that promotes complement binding. So if you put the patient's cells in sugar water and they burst, it means they are missing those protective shields. Nowadays, we use a more sophisticated test called flow cytometry, but the sugar water test is a classic demonstration of the fragility.
Okay, let's wrap up anemias with the big ones. Macrocytic anemias.
When cells are huge, it's usually because the nucleus is lagging behind the cytoplasm in development.
What does that mean?
The cell prepares to divide, the cytoplasm grows and gets bigger, but the DNA isn't ready to replicate and split. So you get a giant cell that can't divide properly. This is the hallmark of megaloblastic anemia.
And this is usually caused by B12 or folate deficiency.
Correct. Both are crucial for DNA synthesis. But the visual clue here isn't just the red cells. They are big and often oval-shaped. We call them oval macrocytes.
What else should you look for?
It's the white cells. You have to look at neutrophils. You see hypersegmented neutrophils.
Normal neutrophils have 3 to 5 lobes in their nucleus. These guys have 6, 7, 8 lobes.
Or more. If you see oval macrocytes and a 7-lobe neutrophil on a blood smear, you can almost guarantee it's a B12 or folate issue. The DNA synthesis problem affects all rapidly dividing cells, not just the red ones.
And this includes pernicious anemia. I didn't realize until reading this that the word pernicious means deadly.
And before we could treat it with B12, it was deadly. Pernicious anemia is specifically an autoimmune disease.
Not just diet.
No. It's an autoimmune destruction of the parietal cells in the stomach. These cells make a protein called intrinsic factor, and you absolutely need intrinsic factor to absorb vitamin B12 in your gut.
So you can eat all the steak you want, but without intrinsic factor, you can't absorb the B12.
Exactly. So the treatment isn't diet, it's bypassing the gut, usually via B12 injections for life.
Speaking of neutrophils, let's cross the bridge to section 3, the white cell defense. These are the soldiers.
The leukocytes.
Yeah.
And they are dynamic. Their appearance changes based on what the body is fighting.
We hear the term left shift constantly in hospitals. The patient has a left shift. What is shifting? Where is left?
It refers to the maturation line of the granulocytes. Imagine a chart where the babies, the myeloblasts, are on the far left and the fully mature adults, the segmented neutrophils, are on the far right. Normally, only the adults are supposed to be circulating in the blood. But in a severe infection, the demand for neutrophils is huge. The bone marrow runs out of adults in its storage pool, so it starts drafting the teenagers.
The bands and metamyelocytes, the less mature forms.
Yes. So the population of cells you see on your differential count shifts to the left toward immaturity. It indicates an active, desperate fight against an infection.
And the soldiers that are fighting, they look beat up. We see toxic granulation.
Right. These are dark, coarse granules in the cytoplasm. It's effectively the cell ramping up its production of antibacterial enzymes to kill whatever it's fighting.
And DILA bodies.
These are these little pale blue oval puddles, usually on the edge of the cell's cytoplasm.
And what are they?
They are aggregates of rough endoplasmic reticulum, basically leftover RNA. It's another sign of rapid metabolic turnover and maturation. The cell is in overdrive.
But, and here is the curveball looking weird, doesn't always mean there's an infection. There are genetic imposters.
This is critical for any lab professional. You have to know the difference. Take the Pelger-Hewitt anomaly.
Okay.
In this benign inherited condition, the patient's neutrophils fail to segment properly. They never develop those 3 to 5 lobes. They stay bilobed, looking like dumbbells or old-fashioned pince-nez eyeglasses.
So they look like bands, the immature form.
Exactly. An inexperienced tech might look at the slide, see all these bilobe cells, count them all as bands, and tell the doctor, huge left shift. This patient has a massive infection.
But the patient is fine.
The patient is completely fine. The key is that every neutrophil looks like that, and there's no toxic granulation or Dooley bodies. The cell is functionally normal, it just looks funny.
But there is a darker version of this called pseudopelgurhuit.
Yes. And this is a very bad sign. If a patient normally has properly segmented neutrophils, and suddenly you start seeing these dumbbell shapes appearing, that is not benign.
It's acquired.
It's an acquired defect. That is often a sign of myelodysplasia or developing leukemia. The cells are losing their ability to mature properly. It's a sign of malignancy, not a harmless genetic quirk.
Then there is Chidiaki-Gashi syndrome. This sounds horrific.
It is a severe autosomal recessive immunodeficiency. The problem is with the lysosomes, the recycling and killing centers of the cell. They can't function properly.
What happens to them?
They fuse together into these giant, monstrous, dysfunctional granules inside all sorts of cells, including neutrophils.
And big granules are bad.
They are terrible. They are too heavy and clumsy. The white blood cell can't move properly. That's poor chemotaxis. And it can't release the granules effectively to kill bacteria. So these children suffer from recurrent, life-threatening bacterial infections because their cellular defenders are effectively paralyzed by their own internal baggage.
We're moving into the most serious territory now. Section 4, malignancy. The leukemias.
This is where the regulation of the blood production system completely breaks down.
The source material draws a very hard line between acute and chronic, and the magic number is 20%.
That's the World Health Organization classification. If 20% or more of the nucleated cells in the blood or the bone marrow are blasts, it is, by definition, acute leukemia.
And blasts are the stem cells, the babies that should never be outside the nursery of the bone marrow.
Correct. If the blood is full of blasts, it means the maturation process is blocked. The marrow is just cloning these useless, immature cells.
And they take over.
They crowd out all the good cells, the red cells that carry oxygen, the platelets that stop bleeding. That's why patients present with anemia, bleeding, and infections, and it happens fast. Acute means rapid onset.
Let's break down the two main types, AML, which is myeloid, and AL, which is lymphoblastic. How do we tell them apart? On a basic level, they are both just blasts.
Visually, it can be tough, but there are some critical clues. In AML acute myeloid leukemia, we look for Auer rods.
They're red needles.
Yes, these are crystallized enzymes, fused primary granules, that form a pink or reddish rod shape in the cytoplasm of a myeloblast.
And if you see one?
If you see a blast with an Auer rod, it is myeloid, period. End of story. Lymphoid cells never make these granules, so they can't make Auer rods. It's pathognomonic for AML.
We also use chemical stains to be sure.
Absolutely. Wow. We use cytochemical stains like Sudan black B and myeloperoxidase, or MPO. These stains react with the lipids and enzymes found specifically in myeloid cells, so AML blasts will stain positive.
And all blasts will be negative.
Exactly. But all L has its own set of markers.
Tell me about all.
Acute lymphoblastic leukemia is the most common cancer in children, with a peak age of 2 to 5. The lymphoblasts are usually smaller than myeloblasts, with less cytoplasm.
And their stains.
They will be negative for MPO and SBB, but they stain positive for a DNA polymerase called TDT, and another stain, PAS, or periodic acid Schiff. The PAS stain is quite distinctive. It forms these coarse blocks or chunks of red color in the cytoplasm rather than a diffuse wash.
And there's an antigen marker, right? CL.
Yes, the common acute lymphoblastic leukemia antigen, now known as CV10, it's positive in many cases of the most common subtype in kids.
I want to zoom in on one specific subtype of AML because the source emphasized it heavily. Acute promyelocytic leukemia, APL, or M3 in the old system.
This is the one every hematologist and lab tech stays awake worrying about. It is a true medical emergency.
And it involves a specific genetic translocation, T1517?
Correct. A piece of chromosome 15 and a piece of chromosome 17 swap places. This fuses the PML gene with the retinoic acid receptor alpha gene, or RAR alpha.
Why is this one translocation so dangerous?
Because the leukemic cells in APL, the promyelocytes, are packed to the gills with Auer rods and procoagulant granules. They are incredibly fragile.
They break easily.
Yes. As they multiply, or when you start chemotherapy and kill them, they break open and dump all these potent clotting factors into the blood.
And that
DIC, disseminated intravascular coagulation. The patient starts forming thousands of tiny clots in their small vessels, which consumes all their clotting factors and platelets, so they end up clotting and bleeding to death at the same time.
But the treatment for this is fascinating. It's not just kill the cells.
No, it's one of the most elegant stories in modern oncology. We use a drug called ATRA, all-trans-retinoic acid. It's basically a derivative of vitamin A.
And how does that work?
Because the genetic mutation involves the retinoic acid receptor, giving the patient pharmacologic doses of ATRA can bypass the genetic block. It essentially forces the leukemic promyelocytes to mature.
It forces them to grow up.
Yes. It pushes them past the promyelocyte stage. They differentiate into mature neutrophils, and then they die naturally through apoptosis. It effectively turns a bomb into a dud without making it explode. It transformed APL from a universally fatal disease into one of the most curable acute leukemias.
That is incredible. Now let's contrast acute with chronic. Chronic myelogenous leukemia, CML.
In chronic leukemia, the maturation process is not blocked. The cells can mature, so you don't just see blasts.
You see the whole family tree.
The whole spectrum. You see blasts, promyelocytes, myelocytes, metamyelocytes, bands, and segmented neutrophils all circulating in the blood at the same time. The marrow is hyperactive, pumping out massive numbers of these cells. The white count can be over 100,000.
And CML has the most famous genetic marker in all of oncology, the Philadelphia chromosome.
The T922. A piece of chromosome 9, which has the ABL gene, moves to chromosome 22 next to the BCR gene. It creates the BCR-ABL fusion gene.
And this gene acts like a stuck accelerator pedal.
The perfect analogy. It codes for a protein, a tyrosine kinase that is constitutively active. It's always on. It's an enzyme that signals divide, divide, divide. It never shuts off.
But this discovery led to a revolution in treatment.
It led to Gleevec, or imatinib. It was the first smart bomb for cancer. It's a small molecule designed specifically to fit into the active pocket of that BCR-ABL protein and turn it off.
It jams the accelerator.
It jams the accelerator. Patients with CML used to have a grim prognosis, needing a bone marrow transplant. Now, most of them live near normal lifespans just by taking a pill every day.
But we have to distinguish CML from a really, really bad infection because both can give you a super high white count with young cells.
Yes, we call a severe infection response a leukemoid reaction. It looks like leukemia, but it isn't. The key is to tell them apart.
And for that, we use the LAP score.
The leukocyte alkaline phosphatase score. This is an enzyme found in normal, healthy neutrophils. When they are fighting bacteria, they are full of this enzyme.
So in an infection.
In a leukemoid reaction, the LAP score is high. The cells are healthy and working hard. But in CML, the neutrophils look mature, but they are malignant and lazy. They are deficient in this enzyme.
So their LAP score is low.
It's very low, or even zero. So high LAP score equals infection. Zero LAP score equals CML. It's a classic differentiator.
We're in the home stretch, Section 5, Specialized Disorders. Let's talk about multiple myeloma.
This is a cancer of the plasma cells.
What are plasma cells normally?
They're the end-stage B lymphocytes. Their whole job is to be antibody factories. In myeloma, one rogue plasma cell clones itself 1 billion times in the bone marrow.
And they all make the exact same useless antibody.
Yes, a single type of antibody. We see it on a protein electrophoresis test as a monoclonal spike, or M-spike.
But the clinical damage is brutal. The source uses the acronym CRAB.
TRAB, CARB. C for high calcium in the blood, R for renal failure, A for anemia, and B for bone lesions.
The bone lesions are what sound the most painful. How do those happen?
The myeloma cells in the marrow produce something called osteoclast activating factor. Osteoclasts are the cells that normally break down old bone. This factor tells them to go into overdrive.
So they just start eating the bone?
They punch lytic lesions holes in the skeleton, particularly the skull, the ribs, the spine. On an X-ray, it looks like the bone has been eaten by moths.
And looking at the blood slide, we see rouleau.
The stack of coins.
Why does that happen?
Because the blood is so full of that abnormal protein, the globulins, it neutralizes the normal negative charge on the surface of red blood cells that keeps them apart. So they lose their repulsion and they stick together in these long stacks.
Compare that to Waldenstrom's macroglobulinemia.
It's a similar concept, a malignancy making too much protein, but the cell is a lymphoplasmacytoid cell, a sort of hybrid between a lymphocyte and a plasma cell.
And the protein is different?
The antibody is IgM.
And IgM is the big one, right? The pentamer.
It's a pentamer 5 antibody units linked together. It's a huge molecule. So when you have too much of it, the blood becomes thick, like syrup. We call that hyperviscosity syndrome.
Sludge in the veins.
Pretty much. And that can cause strokes, blurry vision, all sorts of problems. But critically, Waldenstrom's does not cause the lytic bone lesions. That's a key way to separate it from myeloma.
And finally, polycythemia vera. PV. This is the opposite of anemia, too much blood.
Right. It's myeloproliferative neoplasm, an MPN. The bone marrow is in overdrive, producing way too many red blood cells. The hematocrit can be 60% or higher. The blood is thick and sludgy for a different reason.
And we know the mutation now. It's JAK2.
The JAK2 V617F mutation. It's a specific point mutation found in over 95% of PV cases. It's part of the signaling pathway for the erythropoietin receptor.
So what does it do?
It renders that receptor constantly active. The red cell precursors think the body is screaming for oxygen even when it isn't, so they just keep dividing.
The treatment is ironically simple. Phlebotomy. Just take the blood out.
Therapeutic phlebotomy. It's like being a blood donor, but on a regular schedule to keep the cell count down. But here's the catch.
What's that?
By constantly bleeding the patient to keep their cell count controlled, you eventually deplete their iron stores. So a treated PV patient will often have the indices of iron deficiency anemia, a low MCV, low MCHC, but their actual red cell mass is controlled. It's a necessary induced iron deficiency.
We've talked about so many visual clue shapes, colors, inclusions, but modern labs rely so much on automation. The source material included a scatter plot from an analyzer. I want to visualize this for the listener.
Okay, imagine a graph. On the y-axis, the vertical one, you have volume, how big the cell is.
Okay, sizes up and down.
And on the x-axis, the horizontal one, you have light scatter, how complex the inside of the cell is. Granules, a convoluted nucleus. Those things scatter light.
So let's map the clusters. Bottom left. Small volume, low scatter.
Those are your lymphocytes. They're the smallest white cells with a simple round nucleus and no granules.
Yeah.
They sit quietly in the bottom left corner.
Okay, now top left. Big volume, but still only moderate scatter.
Those are the monocytes. They're the largest white cells by volume, but their nucleus is just sort of folded, not super complex, and they have fine granules, so their scatter is moderate.
Top middle. This is the biggest population.
That's your neutrophils. Moderate size, but their segmented nucleus and their granules cause more light scatter than a monocyte. They are the workhorses.
And the outlier. Way over on the far right. High scatter.
Eosinophils, no question. Their granules are large and highly refractive, like little crystals. They bounce the laser light everywhere. They have the highest side scatter of any cell.
And this scatter plot allows a machine to count 10,000 cells in seconds and cluster them.
Exactly. And if you see a cluster appearing where it shouldn't, like in the ghost region between lymphocytes and monocytes, it might mean blasts or abnormal variant lymphocytes are present, and it flags it for a human to review.
It's amazing how we've digitized the biology, but I want to end on a physiological note, a final provocative thought from the source. We talked about the spleen earlier, how it filters the blood.
Yes, the quality control inspector.
And we talked about sickle cell, where the cells become rigid logs.
Right.
The ultimate irony of hematology lies right here in this interaction.
What is it?
In sickle cell anemia, the spleen works overtime, doing its job, trying to filter out these abnormal, rigid sickle cells.
Right, it traps them.
But the very act of trapping them causes a traffic jam. The sickle cells block the blood supply to the spleen itself. They cause repeated infarcts, small strokes, tissue death within the organ. So the organ dies from doing its job too well.
Over the course of childhood, the spleen becomes fibrotic and scarred, and it shrivels up. By adulthood, most sickle cell patients effectively have no functioning spleen. We call it autosplenectomy.
The body destroys its own filter because the trash it was trying to filter was too dangerous for the system.
Precisely. And this leaves the patient incredibly vulnerable to certain types of encapsulated bacteria like pneumococcus that the spleen is specialized to handle. It changes their entire immunological life.
It's a sobering reminder of the incredible and sometimes tragic interconnectedness of these systems. We started with simple math formulas and ended with organ failure, all driven by microscopic shapes.
That is the beauty and the gravity of hematology. Every cell tells a story.
Well, I will certainly never look at a blood test the same way again. It's not just a list of numbers, it's a status report on a civilization.
A very fragile and yet a very resilient civilization.
Thanks for diving deep with us today.
Always a pleasure.
Keep those questions coming, and we'll catch you on the next deep dive.